Welcome to the briefing room. As a marine safety inspector, I'm going to walk you through the hard data from the 2020 IMCA DP Station Keeping Review. Today, we're doing a deep dive, an explainer really, to look past the superficial excuses and uncover why vessels actually lose position. Okay, let's get to the absolute bottom of these incidents. We'll tackle the 2020 incident statistics, failures versus loss of control, thruster and engine analysis, electrical versus mechanical wear, the human factor and decision errors, and finish up with critical lessons for crews. Section 1, 2020 Incident Statistics. Let's start with the broad picture of the 144 station keeping reports submitted globally over the year. Now, while reporting participation remains high, we all know as an industry that some events still go unreported. But the data we do have, it's an absolute goldmine for preventing future disasters. Out of those 144 reports, a highly concerning 41 escalated to actual DP incidents involving a complete loss of automatic control. We also recorded 79 undesired events and 24 observations. The fact that nearly a third of all reported events resulted in a total loss of DP capability, well, that's exactly why we're analyzing this data today. Looking at the main culprits, a massive 33% of all issues originated from thruster and propulsion problems, which far outpaces power and computer faults. This data points us directly toward our primary mechanical vulnerabilities. Think of thrusters as the muscles of the vessel. When they fail, or when they're pushed way beyond their limits, the situation degrades rapidly. Section 2. Failures versus loss of control. So why do some minor technical hiccups escalate into full-blown disasters with a vessel completely drifts off position? Let's break down the mechanics of how our safety barriers operate and exactly how they fail. We have to clearly separate undesired events, where a system fails but the vessel's redundancy steps in and saves the day, from actual DP incidents. A DP incident means our defensive barriers completely and utterly failed. Grasping this gap between a compromised capability and a total loss of control, well, that's the absolute foundation of dynamic positioning safety. The data shows a terrifyingly high ratio of complete loss of control when the root causes are the environment, position references, or human factors. What this means is that our safety barriers in these specific areas are alarmingly weak. When a human error happens or a reference system suddenly drops out, it bypasses our mechanical redundancies far too often, and that leads straight to a loss of position. Section 3. Thruster and engine analysis. Let's zoom in on our biggest operational offender, the thrusters and engines. We need to understand what's happening under the waterline to cause these massive disruptions. Out of the 47 thruster and propulsion events reported, 23% resulted in the vessel failing to maintain automatic DP control. That is a sharp increase from just 9% the previous year. To give you some context, in one case study, a vessel changed its heading by 15 degrees without even verifying capability. This caused a massive wind load spike, tripped 3 bow thrusters on overspeed, and resulted in a 200-meter drift. These aren't just numbers on a page. They are real, terrifying operational failures. Section 4. Electrical versus mechanical wear. Let's see how this builds when we dig into the secondary causes behind these system failures. The stark reality of vessel upkeep and routine maintenance really comes to light here. Breaking down the secondary causes, electrical faults make up 41%, and mechanical wear sits at 13%. And here's the hard truth for vessel operators. Many of these so-called natural failures actually trace back to a severe lack of basic maintenance. For example, we're seeing things like a single old 24-volt rectifier burning out and taking down an entire port switchboard simply because its quality and age were ignored. I literally cannot stress this enough. Performing maintenance on critical systems like high-voltage circuit breakers or remote input-output modules while actively on DP is an unacceptable risk. In 2020, a crew decided to replace a module online, thinking it was perfectly safe. It directly caused a generator trip and a massive blackout while an ROV and a crane load were in the water. This habit directly caused multiple blackouts in 2020, and honestly, it needs to stop immediately. Section 5. The human factor and decision errors. This brings us to the most unpredictable and, frankly, dangerous variable on the bridge, the crew. Even the most perfectly maintained DP Equipment Class 3 vessel is completely useless if the human at the desk makes a critical error. The data brilliantly illustrates the scope of this problem. The human factor accounted for 26% of secondary causes, representing unintentional behaviors that severely compromised vessel safety. That's over a quarter of our secondary issues stemming directly from the very people we trust to monitor the automation. Now, these unintentional errors don't just happen out of nowhere. They generally evolve through 4 distinct stages: misreading a sensor, forgetting a critical setting, making a bad operational decision, or finally, executing the wrong physical action at the console. Crucially, it's the deliberate decision and action errors that most frequently lead to a catastrophic loss of control. For instance, we reviewed a case where an operator, while just doing routine 6-hourly checklists, inadvertently selected a manual heading change and nearly backed the stern of the vessel straight into a platform. Action errors completely bypass the system's mechanical defenses. Why? Because the computer thinks it's doing exactly what you asked it to do. We really have to ask ourselves some tough questions here. Why are operators deciding to execute risky heading changes or continue drilling when the DP consequence analysis is already screaming about high loads? In one alarming incident, a vessel performing cone penetration testing experienced strong currents. The consequence analysis warned of an off-position event, but they kept adjusting the heading anyway until the thrusters failed, triggering a yellow alert and an emergency disconnect. Section 6, Critical Lessons for Crews. As an inspector, I don't want to just point out the failures. I want to give you the operational playbook to actually prevent them. Let's turn this data into actionable, life-saving protocols. Here is your mandatory checklist for the bridge. Number 1, strictly utilize your activity-specific operating guidelines. Number 2, halt all DP maintenance during operations. Number 3, always ensure a minimum of 3 independent position reference systems. We had a vessel drift off because they were only using 2 DGNSS systems that fell victim to a common mode failure from interference. And number 4, never ever ignore consequence analysis alarms. Ultimately, the most advanced Class 2 or 3 dynamic positioning system is completely useless if the operator lacks the training to manage bridge resources and respond properly to the very first sign of trouble. The automation can only do so much. It's the vigilant, trained operator who actively breaks the chain of errors before an undesired event becomes a major incident. I'm going to leave you with this provocative thought to take back to your fleets. Examine your bridge culture today. Ask yourself if your daily routines are truly preventing incidents, or if complacency is simply paving the way for the next critical decision error. The data from 2020 clearly shows us what goes wrong. It is entirely up to you to make sure it doesn't happen on your watch. Thanks for joining me for this explainer.